last couple of times we've taught it, it has had between 4 and 6 people in it. I'm not sure that we can round up 6 people for the fall. I don't know.
Do you know how many are for sure taking it next semester?
For sure, 2. For sure, 2. How many will? Don't know. Let's hope. Captain.
I think Miranda will take it.
She's not.
I'll try to get her on board.
Oh,
Miranda. Serena.
All right, let's do something new. So the transition metals is synonymous with the D block. That's not completely true. Remember when we looked at group 1 and we said group 1 are called alkali metals and group 2 are called the alkaline earth metals?
Yeah.
Well, that wasn't true either. Like most of group 1 is an alkaline metal. Most of the D block is a transition metal, but not all of it. Not all of it. The extreme ends, the extreme left and the extreme right, don't count because they don't do something that everything else does. So what we see in the transition metals is that they have variable oxidation states. We know full well that if we pick something off the periodic table and it's in group 1, it has a fixed oxidation state. There's a fixed oxidation state of +1. If you're in group 2, you have a fixed oxidation state of +2. If you're in group 3, now group 13, you have a fixed oxidation state of +3. But if you're in the middle of the periodic table, in the D block, these atoms can have multiple oxidation states, and we can do reactions that move from one to the other. All right, so let's go across. You know, I'll probably just take up as much of as I can. No, didn't run out of space. Scandium, titanium. There are a lot of elements named after Scandinavia. Scandium being one of them. And then there's a bunch of elements named after mythological people, as in Titania and Vanadis. And then chromium, from chroma meaning color, which is our first clue. They named this element because it makes lots of different colors. Manganese, and iron, and cobalt. Cobalt is named after a German word for goblin, because when you're trying to mine, I think they were probably trying to mine tin, possibly copper. Yeah, we probably almost said copper. They were probably trying to mine copper, and this kept getting in the way. And they would blame the goblins for putting the impurities in the metal. named after Cyprus. And nickel is named after the devil because, again, you're trying to mine, it was probably copper, and the nickel just keeps getting in the way. So they blame the goblins and the devil for the fact that they couldn't get it. And then zinc. Don't know what zinc means, but it's clearly Germanic in origin. It's a shoutable word, which means it's German. Extra credit. Find a time today where you can shout zinc.
Right now. Zinc! Okay, do I get extra credit?
We've got a D block, and that D block is preceded by potassium and calcium. And then that is preceded by argon. So I have my argon closed shell, and then I have 4s1, 4s2, 3d1, 3d2, 3d3, 3d4, 3d5, blah, 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 blah. Okay. So for the elements, we go 4s2, 4s2, 3d1. Three. I wouldn't be writing this out if there wasn't a point. You know what? I put nickel and copper in wrong. Did I put nickel and copper in there? Good. Well, I'm writing out the electron configuration of it. That's not the electron configuration for copper. Cobalt. Nickel. Copper. Why not? Nine, argon, 4s2, 3d10. Okay. Am I still on screen here? Sort of. Zinc has a filled shell. Because it has a filled shell, it is not going to play the same way as everything does here. It has really only an available oxidation state of +2. All of the transition metals have an available transition oxidation state of +2, because somewhere it was told to you that when you fill the orbitals, you fill the 4s before you fill the 3d. 4s goes in ahead of the 3d. 3 is a lower principal quantum number than 4, so the d's technically are out of order, they're out of sequence. But because because S's are spherical and D's are cloverleaf shaped, you get a better coverage here. More efficient use of your space, lowering of energy. So we're going to put the electrons in the 4s before we put them in the 3ds and build those outbound. And when we lose electrons, oxidation, and we increase our oxidation state, the +2 ion is going to be 4s0 3d10. What we do here is we get a completely empty shell, and we leave that D shell filled. So you've got to fill and empty the 4s before the 3D. You put the electrons in the 4s before you put them in the 3D, and when it's time to take electrons out of the atom by oxidizing it up, you take them out of the 4s first. This means that zinc is not a transition metal. It's in the D block, but it is not a transition metal. We're going to count it as if it is, because it's a D metal, but it has behavior that is much more like a regular main block atom. This is its only available oxidation state, zinc 2+. Scandium. Scandium's over here, and if I make scandium 1, that would be 4s1 3d1. Yeah. If I make scandium 2, now there should be an available 2+, because there's an available 2+ for everything, because I have these 2 electrons right here. I would make 4s0 3d1, and that's still leaving me like a hanging electron here in the D. So scandium really only does the +3. It's really the only one that's available for it. And scandium's +3 ion would be a closed shell, which would be argon. Be 4s0 3d0. Now, this notation of putting 4s0 is okay. You don't have to go argon and then just ignore it because it's not there 3d10. This actually tells the reader, I've taken electrons, and normally what we see is we put electrons incrementally up at the very end, and then we incrementally take them down at the end. Well, this one came out of sequence. So it's okay to tell me that that one's missing. So the 4s0 notation is more than acceptable. I actually encourage it. I'm not sure if it's going to be in our textbook. Although I do really like this textbook. Okay, so that means not scandium, which is going to have a +3 oxidation state, and nor zinc, which only has a +2. But everything else. And we'll spend our time looking at the first row, because the first row of the period of the D blocks, easy. Well, interesting. Lots of stuff going to be thrown up, but not absurdly difficult. All right, let's look at some oxidation states. Titanium. Titanium has a +2. Everything has a +2. And a +3. And a +4. So this has, I'm going to do the in red. You can make titanium like TiO, but it's most of the titanium oxide is TiO2, going to be in the +4. Vanadium, and here's where the book does not tell the full story, because I've got more than my fair share of time spent with vanadium. There is a +2. There is also a +3. The +3 is actually okay. You can handle it for a while, but then it's going to get aerially oxidized. And the 4 and the 5 are the more common. But all of those are available. Chromium. Chromium likes the 2. It likes the 3. And it likes the 6. But that does not mean that you cannot make the +4 or the +5. +4 and the 5 exist, but they're going to be transient. You're probably going to see them sliding. If we do a reduction from chromium 6 to a 3, we might get to see some of this in the middle. And there is a well-known oxidation reduction here that we'll talk about as well. All right, iron. Oh, manganese. Manganese has a +2. In the middle, these are all, there's a +3 that I don't think you're going to have very much success in getting. And then there's a +4. And then there's a 5 and a 6. And then there's a +7. This is permanganate, MnO4-. This is chromate. Those of you who are in organic chemistry, you know these are big oxidizing agents. Permanganate and chromate. And one big click down in oxidizing power from permanganate would be MnO2, manganese dioxide, which would be in the +4. Iron, there is an available 2+ and an available 3+. And there's a 4 and a 6. Don't know that you have to force it to get up there. And then cobalt. Cobalt's nice and easy to work with. It has a 2 and a 3. There is a 4 if you treat it right. Nickel is mostly a 2. There's a +3 and a +4, but it's dominated by 2. Copper is very, very strange. Copper has a +1 and a +2, and then there's a 3 and a 4. Why on earth would copper have a +1? That makes no sense at all. No sense at all, because we lose these 2 electrons. And if we lose those 2, remember, things that are stable in the insides of atoms, empty orbitals, got no electrons in it, you've got no repulsion. Filled orbitals, those are stable, and then half-filled orbitals are stable. But we should be losing both of those, and that's why even like at the left-hand side, these 2 don't really kick in. That's doable. This is better. The book is saying that this is not widely available. Okay. Okay, maybe not as much as that and that. But yeah, you can work with vanadium trichloride. It does need to be stabilized in solution. I always did it under an inert atmosphere, but yeah, you can work with that. But they should all have +2s. Copper does something wrong. Copper's doing this wrong. Here's why it's doing it wrong. See that 4s2 3d9? That is one electron away from being a full shell. When this is a filled shell, then it's clear that I'm just going to lose those 2 electrons and make the 2+. That's the only thing on the table. That's one electron away from being a filled shell. So I'll tell you what, I'll take an electron out of the 1s and put it here. It's like its own little valence hybrid. It has stolen an electron out of the 4s and put it into the 3d, which means that now this is half-filled. Half-filled shells are more stable than just partly filled shells. Partly filled shells are the worst. Filled shells and half-filled shells, or empty shells, are better. So, I've stolen an electron. I've just hybridized it out of the 4s2 into the 3d9 to make it 4s1 3d10. That now means, for the first time, I could lose just that one electron. So the +1 oxidation state, I'm going to write a couple of these down. The +1 oxidation state, why am I looking up a book from the eraser? That's ridiculous. It is Friday.
It's not.
It better be Friday.
I won't show up to open.
Listen, if none of you show up, that means I don't have to show up.
That means you don't have to worry about
The +1 now gets to be 4s0 3d10. That's a win. That's a win. I make an ion, and I keep a filled shell.
Wait, that's maybe the +1?
Yeah, so this is now. This is this now. All right, so let's go and scribble in and see if we can make sense of what's going on here. Nickel. Nickel is going to be +2 predominantly. What's its electron configuration? +2.
Wait, nickel 2?
Nickel
Or
+2.
0 3d8.
Yeah, I steal from the 4s, I leave the d8. Nickel is going to do something that the other atoms don't do nearly as well. The d8 configuration of electrons is special. We'll get to it. Cobalt, if you're the 2+, you lose from the S, and you make 3d7. If you're the 3+, from the S, and you lose 1 from the D. So cobalt has this 3d7 and 3d6 thing going on. For the +2, you get the 4s0, 3d6. And then, okay, he would be an exam question. Explain why in the 2 most common oxidation states of iron, 2 and 3, that if you leave a solution of iron 2 exposed overnight, when you come back in the morning, it's now iron 3. Explain that away. If we go iron 3, what have I got? And is 3d5 notably different than 3d6? In what way is it?
It's 1 less electron.
Okay.
It's not filled anymore. Or I mean, it wasn't filled. Never mind.
How many electrons can the d orbitals hold?
10.
It's half filled. So this is a half filled orbital. Half-filled orbitals are stable. Filled orbitals are stable. Half-filled orbitals are stable because we're presuming there is 1 electron in every available electron orbital, which means this is the position at which there is the least amount of repulsion between electrons in our atom. What's going on at +7? My closed shell configuration at +7, and it's my closed shell configuration at +6. Let's look at +6 here for the ion. That also is my closed shell configuration. So this number builds but maxes out at manganese. Manganese is +7. It's not going to get any higher than that. +7 is the highest oxidation state that we're going to see. These incrementally get higher and higher because oxidation is the loss of electrons. We're building electrons in, but once we get past the midpoint, you start doubling them up. So this is as high as I can go, which means that these are used as oxidizing agents. This one is as well. MnO4 is used as a milder oxidizing agent. Doesn't do all the tricks that MnO4 minus does. All right, there's one other trick on the periodic table. All of them having the +2, not a surprise. They're all supposed to have the +2. Copper has the +1. Chromium is the one that stands out as being +3. Chromium's going to be a little bit different. See this 4s2, 3d4. It's only if you write it out. What's it going to do instead? Going to do what it did with. I steal an electron out of the 4s and put it into the d. I now have this is half filled, both of them. Half filled orbitals. Okay, so we know atoms, we know shapes of orbitals. Do we remember shapes of orbitals? It's not going away. All right, I think. Am I going to erase? I'm not sure I'm going to erase this. Because I might not be done. I'm done with the electron configuration part, but I'm not done perhaps in coming back and pointing, because what I have to do next is explain something that we haven't seen up to this point.
Dr. McGuire.
Yeah.
Vanadium could do the same thing like as chromium, but do the 2 electrons.
Yeah, but moving 2.
Is just less realistic.
Yeah, moving 2 is a bit more effort. It's like, we see other things like this, like, oh, 1,2 hydride shifts. Well, if I just bounce all the way down the fatty acid chain, it's only 22 jumps until I get to the right position. No, you're really allowed one shot at it.
So the only reason why chromium and copper make the 4s1, 3d10, 3d5 is it makes it more stable,
Half filled,
right?
half filled, half filled, filled.
So it makes it more stable. Okay.
Get a little bit extra stabilization. All right, before I go on and talk about the actual interesting stuff, let's just do the regular chemistry. What's happened to Z effective as we move across the periodic table here? Does Z effective get bigger or smaller as you move across the periodic table? We learned nothing from test 1. Z effective, what does Z effective represent? The attractiveness of valence electrons to the nucleus. Why would electrons be attracted to the nucleus?
Because of protons.
Because electrons are negative and the protons are positive, and the protons are in the nucleus. So as I move from left to right, what am I adding to the nucleus?
Oh, nothing.
More protons.
Oh, yes, you are.
Because the atomic number goes up incrementally. Okay. So my electrons are now attracted more. There is a contraction from left to right, meaning nickel is smaller than titanium. Although it turns out, not that much. Z effective increases. From left to right. And what we see is that density and hardness increases. Size decreases, but not dramatically. Not like we saw from, in fact, when we plotted, and we did plot it at one point, the atomic radius from group 1 through group 8, now group 18, and all of the contraction really happened at the first part, the left-hand side of the periodic table. The group 1 and group 2 really got dramatically smaller, then it kind of tapered off a bit. So, yes, the metals on the right are harder, denser, smaller than the atoms on the right, but nothing to write home about. And because they're about the same size as each other, they are kind of interchangeable. Which I think is where the cobalt and nickel, goblins and the devil getting in the way of mining either iron or copper is that these all kind of get in the way. So, what an alloy is? An alloy is a mixture. It's a homogeneous mixture of metals. Like dissolves like. And if you took a metal and you melted it, you converted it into a liquid, that metal liquid could now dissolve other metals. That's what an alloy is. And some alloys have better properties than the individual metals themselves. Being a pure metal is not really an advantage, with the possible exception of gold, because it's shiny and people like its appearance, and it doesn't really oxidize. So it sticks around, but it's very, very soft. So, you know, if you had a nice gold statue and you dropped it, you might bend it, put a dent in it. It is kind of soft. So the alloys might be harder, have better properties, they might be less toxic, they might be more resistant to oxidation. And certainly, we know a couple of things, like putting nickel into iron makes a strong steel. Putting zinc into iron makes it resistant to rusting. So there's a whole bunch of things that are there that are slightly outside the realm of chemistry, because we're into metallurgy and engineering now.
I have a question about zinc.
Yeah.
So, like, they said that to get the most effective sunscreen, you have to have zinc in it.
Zinc oxide.
Yeah, why
Yeah.
is that?
Zinc oxide blocks UV. Lots of other things block UV, but zinc oxide does it just like a thick barrier. Zinc oxide is that white paste. And you put the paste on you. It's like, you know what would also work? paint. And you're at that level, basically you're painting your nose. There are lots of other smart chemical ways of smearing a chemical on your body that has a chromophore that absorbs ultraviolet light into its pi electrons and moves them around. And so now the energy is absorbed by that molecule instead of being absorbed by your cells. The real damage happens when ultraviolet light hits oxygen and excites oxygen into a high energy state, and then that disrupts your cells. Zinc oxide just gets in the way. Brand new type of chemistry. You may have done this in high school. It is not in our general chemistry curriculum. It's called coordination chemistry. And coordination chemistry is kind of hidden. It's right there, but it's sort of hidden. If I took something like, let's take something in the nice, a chromium or a cobalt, in the nice part of the transition part. I take cobalt chloride. And that's a solid. And I dissolved it in H2O. I would make cobalt chloride as an aqueous solution. And everything else that we've seen be an aqueous solution, we just go, oh, okay, all right, so I probably don't have to think very hard about this. I do sort of remember things like this, that if I took some sodium ions, like in maybe sodium chloride, and I dissolved it, and I made this, I do kind of remember that the sodium, because it's a positive, attracts the attention of the solvent, in this case water, and it points its negative end towards the positive ion, and it points its positive end towards the negative. And we just call that solvation. We call these solvation spheres because there's more than one. And you need about 11 water molecules to solvate the sodium. Give or take. Well, transition metals do this as well. When you dissolve them in water, they get solvated, but their solvation is uniform. Here what I have is the cobalt, and that cobalt is going to be surrounded by 6 waters. And somewhere in here, there is a positive charge. And then I have a chloride and a chloride. And you should fully expect those chlorides to be solvated this way, in just a sphere. But the solvation of the transition metal ion is more than spherical. It's geometric. What geometry is that? It's octahedral. This is an octahedral complex ion. The waters, not really they're not bonded to the copper, to the cobalt, but they are attracted, and they are there. Now they can switch out with other water molecules, but there's going to be a water molecule here, and there's going to be a water molecule directly below it and at 90 degrees around it. And because this is different than the chloride, because the chloride is not something that exists naturally on its own, but water does. So this gets a new name. This is a ligand. And a ligand is part of a coordination complex, or a complex ion. We have coordination compounds, complex ions. The ligand is a part of the complex ion that is electrostatically attracted to the central metal ion. It's going to do it through its negative end, so it's got little pairs of electrons here. But the deal with the ligand is it exists in its own right. So it's the part of a coordination compound slash complex ion that surrounds that central atom or ion, which is an ion. And it's different than a counter ion, a chloride or a bromide or a hydroxide, in that it exists in its own right. It can exist independently. Okay. Well, they all do it. Let's have a look at what we have. And this is where coordination chemistry beats out other branches of chemistry, and it starts to. Certainly, it beats organic and biochemistry, is that each of these has its own individual color. Oh, we've got to give this a name. So this is just cobalt-2, right? But now it's dragging 6 waters with it. this gets to be hexa, aqua, 6 waters. But because it's hexa, aqua, you shrink that down to just hexaqua. Cobalt 2, Roman numerals, space, chloride. If this were hexaqua cobalt 2 nitrates, it would be exactly the same thing. If it were hexaqua cobalt 2 bromide, it would be exactly the same thing. Because these, right now, are just counter ions. All they're doing is balancing the charge. They're not attached. So they're not part of the complex. The complex that's going to give what we're looking at right now its color. Okay. Now, everything in the D block makes an octahedral hexaqua ion. And because we have multiple oxidation states in the middle, some of them make multiple ones. Okay, let's go. I'm going to skip scandium. Titanium had an available 3+. So the hexaqua titanium 3, actually I'm going to put this ever so slightly wrong. We use square brackets in chemistry a couple of different times. If something is a reactive intermediate, it's not going to exist, we use it. But it is, square brackets contain everything inside the complex ion, and then the charge lives in here somewhere. So hexaqua titanium 3. Whatever, doesn't matter what, whether it's a nitrate, chloride, bromide, doesn't matter. This is perfect. The vanadium had a 2+ and a 3+. And the vanadium is blue and green. Done lots and lots of vanadium chemistry in my time, and they're different shades. They're more complex. Anybody familiar with what Benetton is? Benetton is a Italian fashion house, and they sell sweaters. And they have a campaign called the United Colors of Benetton that's been going on for 30 years. But instead of making blue sweaters, they make sweaters that are blue, but there's like another complex color in there when you look at it. Like, is that blue or is that green? Or is that purple or is that blue? They do something with the colors. They use a different color palette than everybody else. And vanadium reminds me very, very much of that.
Dr. McGuire,
Yep,
do you know the blue and black or white and gold dress?
I do.
Okay. What do you think?
Depends which photograph I'm looking at. First time I saw it, it was blue and gold, blue and black, whatever, and then I saw a photograph of it later on, and it was white and
Do you know
gold.
why that happens?
I've had it. I've read a paragraph and gone. I think it might be due to the resolution of the photograph, because I looked at one and I could only see it one way, and then I looked at it another way, and only saw it the other way. It's the same with the Lauren and
Yeah, there's like another
Yanni.
one. Yeah,
Oh,
the
yeah.
the hearing thing. Laurel or Yanni or something like that.
Yeah. And the first time I heard it one way, and the second time I heard it differently. I think it depends on what the compression on the radio is when you hear it. Manganese's colors tend to be very, very pale. 2 plus pale pink. We'll do the green. No. And iron. The 2 plus hexachrome for iron is green. But can't tell whether it's green or blue. It's green. And then it doesn't give me more, but there's brown and red here. Cobalt has a famous 2 sets of colors. Cobalt is pink. And it's 3 plus is orange. There is another color associated with cobalt. We're going to have to come back and look at that. And then nickel. Nickel is green. And it's 3 plus, I'm not going to tell you about. And then copper, everybody should know what copper is. That's blue. It's a deep blue that has become known as copper blue.
Are these the same colors that you can do like flame tests with too?
Yeah, same thing, same underlying reason, but now in solution. They all have the same name, or same naming system, and the great thing is that we can track what's happening by the color. Something missing, not in the book. Oh, because it's not the aqua. But if I go out to chromium 6 plus, I don't know that I'm going to get that in solution. I have to be able to get it in solution, but it wouldn't be as the hexachrome. This is yellow. And anybody ever taken a breathalyzer test? Don't answer that question.
My mom bought me a breathalyzer for Christmas.
Good parenting?
Yeah, no, I just turned 21 and it was a little gag gift.
Okay.
So
Before they had the GC based or whatever it is now, common based detectors, they had a little chemical kit that you would blow through a straw into a bag, and you had to completely inflate the plastic bag. And the straw contained crystals of chromate. And the alcohol on your breath will do this in organic chemistry. yesterday. You should have done it yesterday. The alcohol on your breath will get oxidized up to an aldehyde, therefore reducing the yellow chromium through the brown, and once it turns green, you go to jail. Because if you have enough alcohol in your breath to turn chromium 6 to chromium 3 by oxidizing that alcohol up into an aldehyde, then you have too much. So these are all octahedral. I probably shouldn't remove everything. I probably have to keep something up. Where should I leave? Let's take a look. There's something much more complicated is happening. How many d orbitals are there in the 3D?
5.
Who can draw them?
12.
I can draw. What's the first one called?
XY. 3D XY.
3D XY sits between the X and the Y.
YZ.
3DYZ sits between the Y and the Z.
XZ. X squared plus 1 squared. Sorry, there's a 1 minus. You're right. Z squared.
Yeah, Z squared. With a little
Yeah.
circle around it.
Those 5 orbitals are degenerate. What does that mean? Degenerate. They all have the same energy. They are degenerate when they're empty. When they are empty, they all have the same energy. When they are filled or when they're partly filled, they do not. Here's a cobalt. It has waters. Six of them surrounding that cobalt, and its electrons from the oxygens are all on the axes. So, if I am a transition metal and I have these 5 types of electrons, and I have orbitals, and I have electrons in all of them, and then I make an octahedral complex ion, oh, okay. These two feel the brunt of that. Because if I've got electrons that belong to the metal sitting on the X and the Y and the Z axes, that's the X and the Y and the Z right there. These are going to split away and be higher in energy than these. These 3 are non-axial. So here's what we're going to see. I have 5 orbitals. And they're empty. And then I'm going to fill them. And when I start to fill the orbitals, they go up in energy, because I now start to put electrons into them. And then I put them in what's called an octahedral field. And I split them. These are the non-axials. These are the axials. So what I have here are my 3D XY, my 3D YZ, and my 3D XZ. And here I have my 3D X squared minus Y squared, and my 3D Z squared. These two are going to experience more repulsion. Electrons in the axial orbitals are going to be repelled by, here's my finger. These are electrons from the waters, from the oxygens on the water. And they're pointing directly at the metal, down the axial bonds, down the axial axes. So this is going to split this gap called delta. And because that's an octahedral split, that's delta O. That is the energy gap created because you have an octahedral geometry in your molecule. Okay, so Tuesday we will have some kind of in-class activity that resembles an exam. I'll give you a hint. There are things that we did for nitrogen. Lots of different oxidation states. You should probably know that. That's useful stuff. Boranes. I need you to be able to figure out what's going on with boranes. You should also, and that means draw them, sketch them from that kind of plan view that shows the connectivity. Use Wade's rules to figure out whether they are nido, arachno, or closo, and then use Lipscomb's notation to count how many different types of bond are inside that borane. So there's going to be a big boring question. We'll have something on nitrogen. Something on, you have to know that peroxides and superoxides exist and how to identify them, what they look for. And then the bridging fluorides, that's the same as having a bridging hydride in the boranes. That's something that's a big breaking of the rules of what we told you in general chemistry, so that's something you have to retain.
So we're not doing like a weird activity, it's just gonna be red.
No, I'll throw something else in as well. Yeah. So, there will be, I just don't have enough, because everything else is like is an essay question.
Mm.
We don't have enough real short answer questions about, tell me about aluminum. Tell me why aluminum is different than boron. So we'll have a short exam and then an activity, which is the activity that we should have done weeks ago with the close packing thing. And then that'll be that. Okay. And I'll go back and I'll look at my previous year's exams. It's been a long time since I taught this class. And if there's anything even remotely relevant, I'll throw it your way for today, tomorrow.
The test is Tuesday.
No. Let's not go down that path. Because there is a real test coming. Test 3 is a real test, and it is full of fabulous chemistry. What's about to happen here, this is good.
That's racing.
You will like this. It is good. This is great. And with the color, that gap, that's the color. And I can make that gap get bigger or smaller, and I can change the color of my material.
Cool.